Okay. So let me come back. Yeah. Okay. So sorry because I have some problem. Uh, yes, I have some problem with my work. For that, I have to answer all the questions to the client. Okay. And come back to our lecture. So have a look at this slide. You can see. So if you want to, when you do the experiment at the laboratory, okay, you have to measure the such as the, if you come back to this slide, you can see to this. Sorry, yes, to this slide here, you can see this diagram for you to to see how to measure the current, okay, the no load current and also the no load voltage and the power loss here, okay. And of course, if we do the open circuit test, it means that this one is not connected to the load, okay. And as explained to all of you last week, okay, last week here, and for that we can define the transformation ratio of the transformer, okay, denoted by K, okay. Here you know this concept already. And W1 is the turn number of primary windings, and also the secondary winding for W2 here, okay. And of course, so E1 is the rated voltage. The rated voltage is the applied voltage directly to the primary winding of the transformer, okay. And here you can see is the no load current, okay, the load current here also. You can see the no load current here as the I0 percentage is equal to this expression, okay. As I said before, normally the values of no load current is equal to 1 to the 5%, okay, the 5%. And in theory, from 1 to 10, but in practice, maybe I think it's around the 2% is maximum for the transformer, okay. And beyond this, and now so we can define the no load powers and the resistance of the transformer by this expression, okay. P0 here, okay, P0 here. And for this one you got from the measurement, okay. And for that you can define the resistance, okay, resistance of the transformer by using this expression, okay. And in addition, we get the no load impedance and inductance of the transformer by using this expression, okay. And of course, here I would like to show you quickly. If you want to get something in details, of course, when you do the experiment at the laboratories, and the ladies staff will guide you how to measure, how to do, okay. And for our lecture, I show you quickly. And finally, we can define the no loss power, okay, and no load power factor here. So cos phi 0 is equal to P0 divided by E1 multiplied by I0 here. And based on this expression, it's very important for all of you to show. So normally, if you look at, if you read some textbook, or even you go to on internet, you can see, and the people saying that we shouldn't allow the transformer to work with the low load cos phi or with the no load, okay. It means that so when the transformer is connected to the load with the small load, it means that the cos phi of that transformer is very, very small. It's very small, okay. So you see if the cos phi of the transformer is very low, it means that and the electrical system always transfer the reactive power without active power, and this means that it will make the current value is higher than before. It's dangerous for the cable, and also when the current value is very high, it means that the voltage drop is very high, and also the power loss is very high also, and that's what we don't want. And otherwise, you can see for the people, they have to pay much money on the power capacity of the electricity every month. And so that's a reason why for event company, they they want client to work with the high power factor without the small power factor, like this. Okay, and for that, all the transformer is connected to the load. With the full load is okay, but with the low load, I think it's not okay. Okay, in addition, when the transformer is connected to the low load, or we can say that when the transformer is working with the low load, it means that the efficiency is not very high. It's not very high. Okay, it's not very high. And for next, not very high. And for next test is a short circuit test. Okay, you can see here. Have a look at this diagram. And for the previous case, we do the open test, open circuit test, and now we do the short circuit test. It means that the output voltage of the transformer, or we can say the output, the secondary of the transformer is connected together here. You can see and two points connected together, but the voltage at this point is equal to 0. But the current flowing in the transformer is very high in comparison with the rated voltage. So that reason why, if you want to keep the short circuit current flowing in the transformer is equal to exactly the rated voltage, we have to reduce the input voltage of the transformer by using auto transformer here. Okay, or otherwise we can say by using the electrical device which can be changed. Okay, which can be changed the input voltage of this transformer. It means that you can imagine that this is the auto transformer. Okay, auto transformer is connected directly to the source, to the system. Okay, so output voltage of this transformer is connected to the input voltage of this transformer. Okay, because if we don't get the auto transformer here, you can see this transformer is connected directly to the electrical system. For example, here the electrical system voltage of 380 volt, and if output voltage of transformer connected together, it means that the current, okay, you can see the short circuit current in the transformer is very high. Okay, and as I said few minutes ago, if you want to keep the short circuit current in the transformer is a constant. It's a rated voltage. It's a rated current. It means that we have to reduce. We have to reduce the input. Okay, we have to reduce the input. Input voltage of this transformer by using auto transformer here. Okay, and when you do experiment, okay, you have to increase the values of the voltage from zero and to which value, depending on the values of rated current here. Okay, for example, the rated current of this transformer is equal to 5 ampere. Of this transformer equal to 5 ampere. Okay, 5 ampere with the input voltage of this transformer of 380 volt. Okay, and now if we close, okay, or if we connect output, so output wiring of the transformer together, and we keep the same. Okay, we keep the same rated voltage of 380. It means that the values, the short circuit current in this transformer is very high. It's very high. Okay, it's very high. And now so we have to use auto transformer here, connected directly this transformer. Okay, and then we increase from 0 volt to which value? You can see we have to increase. Okay, in simultaneously we have to look at look at the values of the current here, So we start increasing the voltage value from 0 to, for example, 20 volt. Okay, and then we visualize the current value of this one. Okay, if we see the, for example, the current values of ampere met here is equal to 5 ampere. It means that we stop changing. We stop changing the values, the values of this transformer, the values of the voltage of this transformer. We don't have to change anymore. Okay, and from that we get, for example, here 20 volt, and it's corresponding to the short circuit current flowing in this transformer is 5 ampere. Is okay. Okay, if we continue change, or if we continue increase the value of this one, it means that the short circuit current flowing in this transformer is very, very high, and for that it's very dangerous for the transformer. Okay, and that's reason why. So we have to use the electrical device which can be changed, the input voltage of this transformer. Okay, and from the results of short experiment, we can define the I and U and or short circuit current, short circuit voltage, and short circuit power, which can be divided by this expression here. Okay, expression here. I would like to show you quickly about this, and based on this, we can define the short circuit voltage test percentage like this one. Okay, and also the short circuit voltage test for the active component in percentage, and also the qualitor component in percentage here. Okay, and finally we can define the short circuit power factor like this. Okay, and all of you, I advise all of you to remember on this expression. It's very important because all of this will appear on the middle exam or the final exam. So that's a reason why I would like to emphasize that all of you need to remember this one, because when you do the, I don't know, so I don't know where when you come back to the university and to get offline course. Maybe I think in the second week of the November. I think so. And I think so because economic university, all the students of economic university will come back to that university on in the beginning of I think in beginning of November. I think so. But for our university, I don't know. We will see. Okay. And when you do the middle test or the final test, okay, middle term or the final term, you don't, okay, because you don't allow to open the document to do the middle test or the final test. So that's a reason why from now I would like all of you to remember all the things, okay, all the things that I'm teaching you, okay, that I'm teaching you. Okay, and now let me move on to next part, talking about the operating mode of the transformer. Operating mode of transformer in this part and here. So in this part, I would like to show you the energy diagram of the transformer, and also based on the diagram of the transformer, you can imagine the energy flow from the primary winding to the secondary winding. Okay, primary winding to the secondary winding, or otherwise we can say from the input energy to output energy. Okay, and because the process of flowing, energy flowing, you can imagine how many losses coming from the transformer, such as the losses coming from the primary windings and also secondary winding. And in addition, we get the loss coming from the iron core due to the distribution of magnetic field in the magnetic circuit. Okay, let me show you the first part of this section, that is the energy diagram of the transformer, as I said a few seconds ago. Okay, have a look at this one. You can see the energy diagram from left hand side to right hand side. Okay, and this one is the input energy. This one is the input energy and that one is output energy. Okay, so input energy, for example, if you want to transfer the energy from the Hòa Bình province, from the generator system, for example, here we get a P1 plus ZQ1 here. Okay, if you look at this diagram quickly, you can see this one is bigger. You can see here, and this one is bigger than that one. So why that? It's normally for the designer and for the even for the operator and also for researcher. Okay, they expect that output, okay, the output of transformer of any electrical machine is approximately equal to the input energy. Because for doing that, we have to reduce all the losses coming from the electrical machine in general and from the transformer in private. Okay, in private. It means that we have to design, we have to think many ways of reducing the losses coming from the primary winding, from the iron core, from the secondary winding. Okay, from secondary winding. And of course, if you understand very well what I'm saying, you can look at this diagram carefully. You can see we have three different loads. Okay, the first load coming from the primary winding, okay, like this, PC1, okay, with the red color here. And then you can see, due to the diffusion of magnetic flux phi in the iron core, okay, and then we get PFS, the losses, the iron losses here. Iron losses here coming from the eddy current loss. We get PEP, okay? And the rate of energy, that is the electromagnetic power, PDT here, okay? From the primary winding to the secondary winding. So in the secondary winding, you can see we get the PCU2 is a copper loss, okay? From the secondary winding. And then the rate of energy, we get the P2 here. Okay, so in the middle term, for example, is problem in the test, they will ask you. For example, they give you the values of P1, PCU1, okay, for example, even for PEP here, PFE here, okay, they ask you to calculate, okay, to compute the electromagnetic power. It means that they ask you to compute PDT here, okay. How to compute? Okay, for example, if you look at this one, if you look at this diagram, assuming that they give you P1, PC1, PP here, okay, it's very easy for you to compute PDT. So why that? You can see, if you look at, for example, you are standing at this position here, okay, and now you look forward to the left hand side here. Okay, you look forward to the left hand side here. You can see the PDT is equal to P1 subtract PC1 PP1 here. Okay, of course, because and this value and that value and that value given you in advance. Okay, and now it's very easy for you to deduce PDT here. Okay, and otherwise, and in addition, for example, if you if they give you this value, that value, and this value, and they ask you to compute the no loss coming from the iron core PEP here, and also it's very easy for you to calculate this value, okay, this value, and PEP is equal to, you can see here, P1 subtract PDT subtract, you can see here, PC1, okay, and in addition we can compute PC1 if they give you PEP and PDT and PU in advance, okay, and for that, and of course, and now if you look forward to right hand side, you can see here, and for example, PDT is equal to P2 plus PCU2 here, Okay, and otherwise, if you want to calculate PCU2, of course, if you know the PDT and P2 in advance, okay, and also you can compute this one, okay, and based on this energy diagram, okay, we get some different case like this, okay. For example, if the load of this transformer is the inductive load, it means that we get the Q2 is bigger than 0, then Q1 is larger than 0, and for at that time it means that the reactive power of the transformer is transferred from the primary winding to the secondary winding. It means that for this transformer it taken, or we can say reactive power is taken from the electrical system to the transformer, okay, for the inductive power, okay. Like before last week when we were talking about the vector group, okay, vector group of the transformer, you can see the values of U2 is lower than the values of electromagnetic force, okay. It means that the transformer is connected to the inductive load, okay, inductive load. And for this case, it means that the cos phi of the transformer is very low, okay. And now if we want to support the cos phi of the transformer, or otherwise we can say if we want to increase the cos phi of this transformer, okay, we have to take the reactive power from the electrical system, or otherwise we have to design the capacitor for this machine, okay. And for second case is that, so if the load is a capacitive load, phi is smaller than 0, if we get the Q2, okay, Q2 is smaller than 0, and for that we get two different branch, two different case. So if Q1 is smaller than 0, it means that the reactive power is transferred from the secondary side to the primary side. For this one you can see, and for this one you can see the case of the capacitive load. So why that? If you look at, if you remember the case of last week when I was teaching you, you can see if you look at the vector group, you can see if the values of the voltage when the transformer is connected to the capacitor load, U2 is always bigger than electromagnetic force. So that's the reason why when we come back to this case, you can see the reactive power is transferred from the secondary winding of the transformer to the primary winding of the transformer, or we can say you can say the transformer transfers the reactive power to the electrical system, okay, to the electrical system. Yes, and if the Q1 is bigger than 0, it means that the transformer will take reactive power from the both sides of the transformer. The one side is from the electrical system, and another side is the secondary winding. Is the secondary winding. Okay. Yes. And now, so we are talking about the because based on the variation of the load and leading to the trends of the output transformer, and in order to validate, okay, in order to appreciate the voltage, okay, and the voltage value of the transformer, okay, and now we move on to the next part, talking about the voltage variation and regulation of the transformer, okay. And for this one here, first of all, I would like to show you about the voltage variations, okay. As mentioned above, the primary voltage denoted by U2. You know this concept already, okay, because all of you is not trained for this. And you know, so this voltage depends on the values of the load current, okay. The load current which can be the inductive load or the capacitive load, depending on the application of the transformer in practice. Okay, and for that we can compute the voltage variation denoted by delta U by this expression here. Okay, delta U is equal to U0 subtract U2 here. Okay, and U0, you know this already, because U0 is corresponding to the electromagnetic force of the transformer with no node current. Okay, and of course U2 here. Of course U2 here. U2 is saying that and the transformer is connected to the either capacitive load or the inductive load. Okay, if you want to get the value in percentage, we can apply like this. Okay, and of course, if you look at this equation, it's simply, but it's very important for all of you to apply this to solve the problem. So that's, I would like all of you to keep it in your mind. Okay, keeping it in the mind. Okay, yeah, please keeping it in the mind. Okay. Yes, and now you have know well about the concept of voltage variation delta U here. Okay, I would like to show you the vector group of this one. Okay, maybe I think for this one I would like to I'm trying to use whiteboard. Okay, whiteboard to draw. We'll see whiteboard. For doing that, I would in order to do that, I would like to stop sharing the slide, and then I'm using whiteboard here. I think so. Yes. I don't know. I don't know why. Yes. Okay. 1 minute, please. Yes. Okay. So because software is loading whiteboard. There's some problem with this one. I don't know why that. Maybe I think there's some problem with the signal. Stop presenting, but here. Okay. Whiteboard. Okay, loading. Yes. Yeah. Okay. Yes. Okay, so I'm seeing something. I'm seeing something on whiteboard or not? For example, if you can see like this, the vector. Yes.
No, we can't.
Okay, right. Nice. Okay. Okay. Now, so if you look at this slide, okay, I'm drawing. For example, here I'm using maybe I here delta U. Because here delta U here. Okay, delta U is a voltage drop. You know already in percentage. Maybe I think I'm using the sorry. Yes, maybe I think I'm using this. Okay, delta U here. You can see delta U. Okay, delta U. Maybe I think percentage here like this. Okay, and now you can see this axis is we get beta. Okay. Oh, sorry. Okay, and maybe I need to write beta like this. Okay, and beta here you can see. Okay, you should remember this expression. Beta is equal to 2 divided by the, and here a rated current. Rated. Rated current. Okay, and RATED or rated current. Okay, you can see this one. It's a load current. Okay, you can see here is a load current. Okay, load current. Maybe I think here, so it's a load current. You can, it's a load current. Okay, it's a load current here. Okay, and now you can see it's a beta. This axis is the load current, and if you get the different, you get the different load. For example, here you can see, and like this. Okay, and here is corresponding. The cosine is corresponding like this. Okay, it's equal to, for example, here you can see 7. Okay, and here the cosine is equal to 1. Okay, for example, here you can see the cosine equals to 7 here. Okay, and of course I would like to show you. So for example, if the same values of beta, the same value as beta, you can see, for example, here. Okay, and you can see the same value. The same values of beta, but with different type load. Okay, for example, here you can see when the cosine equal to 1, it means that the transformer is connected to the receive load. Okay, receive load. Okay, you can see we get here, for example, we get this, yes, because here we get a delta UR, for example, UR for the resistive load, UR. Okay, and of course here you can see, here we get, if I write like this, delta U and here. Okay, and of course you can see here we get delta UC here. Okay, you can see it means that with the same load, okay, with the same load value, okay, with the same load value, you can see we get a different, we have the different voltage drop. We have the different voltage drop like this. For example, if the transformer is connected to the inductive load, you can see inductive load, you can see we get voltage drop is the delta UR. Okay, here is smaller than the delta UN, UN here, L, and delta UL here. And because here you can see for the cosine of 0.7 is corresponding to the inductive load. Okay, you can see, and when the transformer is connected to the inductive load, and the voltage drop is bigger than inductive load case. Okay, and in addition, we get when the transformer is connected to the capacitive load, you can see the output voltage of transformer is very high in comparison with the rated voltage. Okay, rated voltage here. Okay, and this the vector group showing you that at the same load, but with a different load, we get the different voltage drop, where we see the voltage drop of inductive load is very big. Okay, it's bigger than to the inductive load and capacitive load. Okay, and of course, and for the capacitive load, and you can see the voltage drop is the negative. It's negative without being positive. So why that you can see here. So that's the reason why when we apply, when we connect to the capacitive load, output voltage of the transformer is higher than the rated voltage, okay, because this concept you know already. Okay, now let me come back to our slide. I would like to show you. You can understand here. Yes. Okay, you can see with the different different loads, and here with the cos phi is equal to 1 is corresponding to the inductive load. Sorry, the resistive load you know already, and here for the inductive load, and here for the capacitive load. Okay, and beta, the values of beta you know already, because I have just show you in the whiteboard. The beta is equal to I0, I2. I2 is the load current divided by the I divided by I rated. Okay, the current. Okay, and for that we get as this one. Okay, and with the same, for example, the beta is equal to 0.8 here you can see, and we get a different drop voltage if you look at this axis. Okay, and the idea that the voltage drop, okay, depends on the load factor. Load factor is beta here, and also the cos phi, and also type of load, inductive load or capacitive load. Okay, and based on this, because of the different load, leading to the output voltage of transformer being lower or larger than the rated voltage. Okay, and the question is that if you want to give the output voltage of the transformer as a constant, with even with a different load, and how to do, okay. And I said before, because maybe I think last week or last two week about this way. Okay, or this way for any transformer, even for the distribution transformer or the transistor transformer, or step down transformer or step up transformer. If you want to keep the output voltage of the transformer as a constant, it means that we have to change. Okay, we have to change the turn number of the winding. But I would like to re-ask all of you again. Okay, and which winding for us to change the turn number? Do you remember? Because I think the last week it's the same questions as the last week. Okay, for example, if you want to keep the output voltage of the transformer as a constant, and of course you know well, all of you know well, we have to change the turn number of the winding. But the question is that the either primary winding or the secondary winding. So why is that? Please answer my questions. Please answer my questions. Who can answer my questions? Okay, maybe I think I would like to call on a few. Hoàng Huy Tuấn. Hoàng Huy Tuấn. He's absent today. Okay. I would like to call another student. Hoàng Ngọc Anh.
No, I don't know.
You don't know?
Yes.
You don't know, or you don't understand my questions?
I don't know.
You don't know. Okay. Hoàng Vinh. Hoàng Vinh. You know my questions or not?
Sorry, sir, I don't know the answer.
Okay. Okay. So it means that you haven't, okay? You haven't reviews, okay? You haven't reviewed my lecture so far, okay? So far. Of course, I think you should be careful, okay? You should be careful with this theory. So why that is very important? It's very, very important. That's what I would like to emphasize. So once you don't understand theory, okay, even when I give you the practice or the problem, okay, easier, but you don't get the answer. You don't get the answer. Okay, don't get the answer. Okay, let me repeat the theory. Last week we did. Okay, and here, come back this one. If we want to give the output voltage of the transformer as a constant, it means that we have to change the number of the winding getting the high voltage. Okay, so why that? Because I already explained to all of you that. So when the winding getting a high voltage, it means that the current value is very low. And for the current value is very low, it's very easy for the designer, for the factory to produce the contact of the point, the contact of points. Okay, and then so when we change the turn number of the winding, there will be no the arc between the point to point, Okay, so that's otherwise. So for the high voltage winding, is all the way. Okay, you can see it's all the way located outside of the low voltage. And for this way, it's a little bit easy for the operator to change the turn number as a winding. Okay, we have the two reasons. For changing the turn number of the high voltage winding, and I am explaining to all of you. Okay, yes, I think all of you should remember this concept. Okay, and in general, there are some regulation windings in transformer with the different level. Okay, and of course you can see the voltage regulations. Okay, voltage error is mean that we have to change the voltage level of the winding. Okay, we get the different. Okay, we have the different levels like this, different level like this, and plus, and you can see here there's something wrong. Something wrong here is a plus and minus. Okay, you can see because here I think because of the font in the PowerPoint, so that's a reason why you cannot see exactly the size of this one. Okay, let me explain to all of you. And the sign here plus and subtract, plus and minus. Okay, plus and minus 2.5%, and of course in the same way, plus and minus 5%. Okay, it means that we can change. It means that we can change the different level of the voltage of the transformer, and sometimes the voltage level like minus 2.5% or the plus 2.5%, or either minus 5% or plus 5%. Okay, depending on the state of the transformer connecting to the load. Okay, connected to load, inductive load. For example, inductive load, it means that the output voltage of the transformer is reduced too much. Okay, and for that we have to change a lot by increasing or reducing the turn number of the high voltage winding. Okay, high voltage winding. Okay, even next time, okay, next 2 years, when you graduate from this university and you will work for the company as a operator. Okay, operator, of course you have to visualize, okay, you have to visualize the voltage value of the transformer. Even you can use the control unit to monitor, okay, to supervise, okay, the state of operating of the transformer. But you have to understand theory, okay? Not only for this electrical machine, but also for other device, even for the control system or the electronic system also. Okay, that is a concept for all of you to understand. Okay, and otherwise, I have just explained to all of you. Okay, voltage regulation. Okay, we have to use so we have to do in the primary winding getting high voltage. Okay, you understand very well. So why that I don't have to repeat anymore. Okay, and for next slide, I'm going to show you how to compute the transformer losses. The transformer losses, and of course, up to now, you can tell me how many losses appearing in the transformer. Okay, we have 3 main losses coming from the transformer. The first one coming from the primary winding, that is the copper losses denoted by PC1. Okay, and of course we can come back to this expression later. Okay, and the first of all, we are discussing about the transformer loss. And for the no load losses, due to the distribution of magnetic force, due to the distribution of magnetic field in the iron core, and for that we get the hysteresis and eddy current losses. And now, how to define the power loss of iron core? Okay, based on the hysteresis and eddy current losses, we can define the power losses denoted by Fe by this expression here. And of course, this method is the analytic method to compute the power loss. But in practice, if you want to simulate the distribution of power loss of the transformer in general or the electrical machine in detail, for example, okay, if we apply the analytic method like this to compute, and of course the error is very big, because, and for this methods, we cannot compute the freezing or the leakage flux of the transformer, because for the freezing or leakage flux of the transformer must be regulated. And of course, we only compute the main magnetic flux flowing in the iron core. And for the freezing and leakage, okay, we have to assume that it doesn't influence to the main flux. And for that, we get something like, some trouble like the errors, inaccuracy, okay, accuracy. But in our lecture, we accept, okay, to apply this equation to compute the power loss of the transformer, okay. And in this expression, you can see some parameters such as, so P1 divided by 50, okay, is the dissipated power loss at the frequency of 50 Hz when the magnetic flux density being equal to 1 Tesla here. Okay, you should remember this concept. Okay, of course, you can see BT, BG, and GT and GG is the respectively magnetic flux density and weight of the core yoke of the transformer. Okay, and this expression is also very important for all of you to remember. Okay, because in the future, if they ask you to compute the power loss, okay, power loss due to the hysteresis and ethical loss. Of course, if you don't remember the equation or the formulation, okay, so I think you don't know how to apply this yes, the expression to solve the problem. Okay, for that. Okay, and the first load is the power loss. Okay, power loss. And now, so we are continue. We are considering for the different loss coming from the copper loss of the primary winding and the secondary winding of the transformer. That is the PCU1 and PCU2, and I said before. Okay, here you can see PCU1, PCU2, and of course PP we defined in advance here already. Okay, and by summing up all the loss of the transformer PCU1, PCU2 plus PPI, we get a total loss here. Total loss here. Okay, and this one appearing from this one is a copper loss appearing from the primary winding, and of course here for the secondary winding, and this one, you know, we get that one. And of course normally when you look at carefully in the nameplate of the transformer, you can see PP, they give you in advance. They give you in advance, so that's the reason why. Because if you remember that, and in the previous slide, I was teaching you, okay, because I was teaching you about the way of doing the experiment and how to measure the no loss losses by using the watt meter. Okay, you know, PFE here is equal to P0, written in the nameplate of the transformer, okay. And by that, so when you do the exam, of course you have to take this value from the nameplate of the transformer, okay. Because when I give you the middle term or the middle exam, okay, even for the final exam, okay, of course I will give you the nameplate of the transformer, show you all the main parameters of the transformer, okay, such as the power, the no load, and the current, and the voltage, and also vector group of the transformer, everything. Okay, beyond that, you can, if you solve the problem, you see, and of course some relating parameter, of course you have to take directly from the nameplate for solving the problem. Okay, so solving the problem, because I know that, so even I repeat many times, but at the middle exam or the final exam, I think there are still several students asking me that. Okay, asking me that. When I solve this problem, I don't get enough parameter to solve, but everything written in the nameplate of the transformer. Okay, because every course, okay, they weren't in the class, so that's the reason why at the middle exam or the final exam, they always give me some questions about that. Okay, and of course once we get the total loss, and now it's high time for us to compute the transformer efficiency. Okay, how to compute? Okay, let me go to this slide. Okay, go to this slide. You can see the transformer efficiency, which can be defined by this one. It can be defined by this one. You can see the neta percentage is equal to P2 divided by P1. P2 is output power of the transformer. P1 is input energy, you know already. Okay, and the question is that how to compute the P2. P2 is equal to P1 minus subtract all the total loss of the transformer. Okay, and total loss transformer, which can be defined by this one. Okay, by this one here. Yes. Okay, and of course here. And the question is that, and I said, the question is that if you want to get a high values of the efficiency, it means that you can see the total loss, of the transformer must be very, very small. Okay, must be very, very small. Okay, if you want to get the sum of loss here, it's very small. It means that, let me come back. It means that PC1, PC2, PFE must be low. Must be very slow also. Okay, and this one depending on the material technology and also depending on the designer, depending on designer. Okay, the first of all, if you choose the good materials for producing the transformer, it's very nice. And also if you design, if you design optimize, if you design this transformer in optimization, I think, and the total loss must be reduced. Okay, so once the total loss must be reduced, it means that the efficiency of the transformer is higher. And of course, for the EVN company, they will regulate for the transformer when it's connected to the load. They have to answer that about the efficiency. So if the efficiency of the transformer is not answered as a regulation, okay, and they don't allow to connect it to the electrical system, okay. And of course, for the factory, when they produce the transformer, they have to take care of the regulation of EVN company, okay. For example, if they regulate the efficiency of the transformer must obtain some 95%. 95%. For example, here 95%. It means that the transformer produced from the factory must be obtained until the 95%. Okay, if they don't obtain 95%, okay, of course the transformers cannot connect it directly to electrical system. Okay, electrical system for that. Okay, and in addition, we get another new concept. PN is a short circuit power losses is equal to PC1 plus PC2 here. Okay, I think you should remember also, because sometimes in the test, okay, in the test they will give you some parameter, of course, and they will ask you how to compute the short circuit power losses. Okay, of course you have to know well this concept. Okay, it's very easy for you to compute even in few seconds. Okay, and also here you can see PCU is equal to Rn multiplied by square of I2 here, and equal to this one. Okay, and for the beta, it's a load factor, as I said before. Okay, I said before already. Yes, and B2 is equal to I0 divided by I rated current here. I rated. Yeah, because I rated current here. So I2 is the current flowing in the load. You know already, current in the load depending on the inductive load or capacitive load. Okay, a capacitive load. Okay, of course we get beta here. Okay, and the question is that, because normally is when they ask you how to, if you want the transformer to obtain a maximum efficiency when the power loss of the iron core is equal to exactly the copper loss, it means that we get the P0, okay, is equal to Pn here. Is at that time the transformer will obtain a maximum efficiency. Okay, efficiency. And this one is very, very important. Okay, for all of you to answer the question in the middle term or the final exam. Yes, okay, final exam. Yes, for the final section of this chapter, okay, we are talking about the three-phase transformer. Okay, so normally after completing each chapter, I would like to give you a problem for you to solve. Okay, maybe I think for next week, because and for this part of this for this section of this chapter, maybe I think it will take 2 course or 3 course. I don't know. Okay, I don't know. We will see. Okay. Yes. And for the three-phase transformer, okay. And now, so I think before talking about the three-phase transformer, I would like to ask One of you about the single phase transformer. What is the difference between the single phase transformer and three phase transformer? Who know my questions? Please answer my questions. Yes, we are currently in three phase transformer. Okay, and according to the opinion, please answer my questions. What is the difference? What is the difference between the single phase and the three phase transformers? Who know my questions? Feel free to answer my questions. Don't hesitate. Even you answer wrongly. I would like to ask one of you. Vương Viết Hùng. Vương Việt Hùng hay là Vương Viết Hùng em nhỉ?
Vương Việt Hùng.
Okay, please answer my question.
I think the difference is the number of coils used in the single phase. To use two coils each for a primary and a secondary. But in the three phase transformer, we use six coils, three for primary and three for secondary.
Yes. Okay. Anything else? Anything else? Okay. Yes, you are talking about the construction of the transformer between the single phase and the three phase transformer. Yes. For example, you are talking about, for example, the single phase is a single phase consisting two squaring. Okay, low voltage squaring and high voltage squaring. Okay, and for the three phase of the transformer, including the six squaring, for example, like this. Okay, and here, yes, of course, for the yes, for the construction of transformer. And how about the main parameters, for example, such as the voltage, current, the vector group, and such.
I can only think of is the three-phase transformer usually used in a transmission system when the power is supplied by a three-phase generator, which each phase is 120 degrees apart.
Yes, okay. It's also a good idea. Yeah, all right. Nice answer. Okay, thank you. In order to answer the questions clearly, okay, let us come back to our lecture. Okay, to our lecture to see what is the difference between the single phase and the three phase transformer. Yeah, correctly. Okay, you are still seeing the slide on the computer? Yes?
Yeah.
Yes, okay. And here you can see. Have a look at this slide quickly. Okay, slide quickly you can see. For example, if we get like this. And of course, in practice, you want to create three-phase voltage system. Okay, you have to use the three-phase transformer or the three single-phase transformer. We get two different way. We get two different way of creating the three-phase voltage. Okay, the first So either we can use, you can use a three single phrase transformer like this. Like this. Okay, you can see like this one. Or we can use a three-phase transformer like this one. Okay, and of course you can see, if you remember that, I think from beginning of this course I would like to show you about the single phase of transformer. Okay, three single phase transformer is, we have to match, we have to match three single phase, okay, of the transformer, and then we can connect, okay, for example, phase A, phase B, and phase C in delta or in star, or depending on the type of electrical system. Okay, and of course have a look at this one. You can see, for example, here one single phase. Okay, with single phase transformer, single phase transformer, single phase transformer. And now if we want to get the three phase voltage upward, we have to match three single phase transformer together by connecting primary winding or the secondary winding in delta or in star, or in delta or star. Okay, you can see, for example, here, if you look at phase A, of course, beginning of phase A, okay, the end of phase X, okay, and of course we get phase B, Y, okay, because you can see here for the, yes, for the first or the terminal of this one, you can see here, and of course we get phase C and Z, and of course for each phase we get two different winding, the primary winding or the secondary winding. Of course, let me explain to all of you again. For phase A, we get the primary winding with, for example, high voltage winding or the low voltage winding for the secondary winding here. And of course, we get a phase B, okay, the high voltage winding, low voltage winding, phase C, the high voltage winding, low voltage winding. So when we are talking about the high voltage winding for primary winding, okay, it's a low voltage winding for the secondary winding, it means that this machine is step-down transformer. Okay, step-down transformer, it means that for the high voltage is connected to the electrical system, as a low voltage winding is connected to the load. Okay, and here, okay, you understand very well the three single phase transformer by matching from the three single transformer. Okay, and of course here we are matching in two dimensions. In two dimensions, or we can say in the 2D plane. You can see like this one. And now if we match three, okay, three things together in the three dimension, okay, in three dimension like this one, okay, and for the finger B, for finger B, it matches three single phase transformer in three dimension. You can see like this, okay, and of course it's very easy for you to recognize phase A, okay, A is for the, for example, for the primary winding, and in capital, you can see here's the letter in the, yes, the letter is capital here, okay, and here is the normal, you can see A and X, and the capital A and X here, okay, X, and of course for phase B here, and of course for phase C here. Okay, so when we match three single phase together, of course we get the same coil, okay, the same coil of three single phase here, okay, yes, and of course for finger B, so that when we change three single phase transformer into one three phase transformer, okay, you can see, and the core M and is presented by phase A plus phase B plus phase C, even we are writing for the note M, okay, and of course and for the and of course, because you can see, and because of the symmetric magnetic circuit, okay, magnetic circuit, so that means that the phase A plus phase B and plus phase C is equal to 0, and for that we can, and the core M end can be regulated, once the core M end can be regulated, it means that we can push phase A, phase B, phase C in the plane like this, okay, like this, without appearing the core M end anymore. And for now, so when we consider the three-phase transformer, okay, of course we have to consider the three-phase transformer like this, okay. And of course, if we consider three single phase matching together, and of course we have to consider the finger A like this, okay, finger A like this. And for that, if you go to the side, you can see sometimes we get a three single phase transformer, okay, of course for the and for the large, for the transformer with very high capacity, okay. And of course we also see the three-phase transformer with a lower capacity, okay, lower capacity, depending on the application of the transformer in the side, okay, in the side. But for example, for the transmission transformer, they usually use a three single-phase transformer, okay. And of course, for the distribution transformer, they can use a three-phase transformer, and I show you in the figure C here, okay. This thing here. And of course, in order to show you clearly, I would like to show you some picture to easily visualize, okay. We have two choice, okay. The first choice like this, okay, you can see, and here three single-phase transformer, and this picture only appear in the Ho Chi Minh City, because in Ho Chi Minh City they easily use this type of station. For example, phase A, phase B, and phase C, okay, in the electrical port here, okay. And of course you can see here three-phase transformer, here, you can see, yes, three-phase transformer. You can see what is the difference, okay, different. And of course in the middle term or the final exam, and sometimes they will ask you what is the difference between the single-phase transformer and three-phase transformer, or they can also ask you to answer the question like this: what is the difference between the three single-phase transformer and three transformer, okay, three transformer. And of course if the middle term is a multi-choice, of course they will give you the answer already, and of course the responsibility is to select the best answer for the questions, okay, for the question, yes, for the question, okay. And here you can, yes, for next slide I would like to show you quickly about the drive transformer used in the distribution line of 150 kilovolt, okay, and the voltage level 6, okay, or 6 for the high voltage, and 0.4 kilovolt for the low voltage, of course. And of course the vector group is delta, you can see, and the primary wiring is connected in delta, of course. For the secondary wiring is connected in star with a neutral point here, okay, yes. I think before analyzing in detail this slide, I would like to give you 10 minutes for the time break, and then we come back to our lecture, okay, yes.
Yes.
Yes, okay, we come back to
Yeah.
our lecture in 10 minutes, okay, yes. Okay, so let's come back to our lecture. Yes? Are still hearing something for me? Yes.
Yeah.
Yes, okay. And okay, come back to our slide. I would like to show you. Okay. And here is a picture show you the nice transformer, that is the dry transformer used in the distribution line. The capacity of 150 kVA. Okay, kVA because you need a kVA. Okay, so normally some textbook written in VA or kVA. For the high capacity, they use kVA. Okay, and of course a voltage level of 6 kilovolt. Okay, and for the high voltage and the low voltage is 0 and 0.5 kilovolt. Yes, of course. And here we can see the three core. Okay, 3 core here for each core, including so phase A or phase B or phase C. Here you can see here is winding. Okay, and just to show you quickly about the night picture. And now, and for next part is very important. It's very important in my opinion. That is the three-phase transformer connection. Three-phase transformer connection. Okay, and before doing the vector group of the transformer, okay, we need to be familiar with the concept of connected winding simple. Okay, simple. Okay, you can see here normally for the high voltage winding. Okay, and the heat up windings is A and B and C. And for the high voltage winding, okay, how about the end of windings? End of winding, for example, here you can see the A and H, B and Y, and C and Z. Okay, and of course, if the winding if the connection winding of the transformer getting a neutral point, we get the N or 0, depending on the type of transformer. Okay, and sometimes for the neutral point of transformer is the N, denoted N, or the 0. Okay. And of course, how about the medium voltage winding? Okay, so for the medium voltage winding, we keep the same, the capital letter here, Okay, you can see here, but we use a subscript M here. M is the medium voltage. Okay, for example, for the medium voltage winding, for high voltage winding, AM, of course, XM, BM, and YM, and CM, and ZM. Okay, and for the low voltage winding, how to denote? You can see the normal letter. Okay, normal letter A and H and B and Y and C and Z. And of course, if you get the neutral point, we get the N, okay, or 0 here, N or 0 here. Yes, and based on the connection winding of the transformer, we get the different connected winding groups. Okay, of course, for each winding of the transformer, we can connect. Okay, we can connect in delta or in star. Okay, in delta or in star. Okay, and for next tonight, I would like to show you the way of connecting for different connected winding. Okay, and the first, as I said before, and for the primary winding, which can be connected in delta or in star. Okay, and for that we get the four basic connections. Okay, the first one is both primary and the secondary side of the transformer are connected in star. It means that we get star and star. Okay, so in some textbook written like this. Okay, star or the in capital or the normal letter like this. Okay, and the second way is that for the both primary and the secondary side connected, okay, are connected in delta. It means that we get delta and delta, or we can write another way, and D in capital or the normal D like this. Okay, and for third case that the primary wording is connected in delta or in star. Okay, and here is connected in star. And of course, for the secondary wording is connected in delta, and for that we get a star or delta here. Okay, or we can write like this, star or normal D like this. Okay, and the final connection of the transformer is that the primary wording is connected in delta. Okay, and of course for the star is connected in secondary wording is connected in star, and for that we get the vector group like this. Okay, and of course, and here you can see we get 4 basic connection for the type of wording of the transformer. And now the idea that and how to define the number of the vector group of the transformer, and what is the number. Okay, and let me move on to next slide. I would like to show you the number of the connection. Okay, have a look at this one. Have a look at this one. You can see. Have a look at this one. You can see. Of course, if you look at this one, if you look at this figure, okay, if you look at this figure, from the left hand side to right hand side, as I said before, we get 4 different conditions of the wording. Okay, conditions of the wording. And the idea is that how to define the number, for example, here number 12, number 11, number 11 here. Okay, the first of all, I would like to show you the way of defining the vector group of the transformer. In order to determine the vector group of the transformer, we have to define the phase displacement. Okay, or we have to define the phase angle. Okay, the phase angle between the line-to-line electromagnetic force of primary winding and the secondary winding. It means that you have to build the vector group. You have to build to define the line-to-line electromagnetic force of primary winding and the line-to-line electromagnetic force of secondary winding. Okay, and for that we can define the number like this one. Okay, for example, if you forget, okay, and now if you forget the number like this, of course, if you look at this one, it's very easy for you to get. Okay, of course, the type is a type of connecting winding here like a star. Okay, it's very easy for you to recognize. Of course, here star is for the high voltage A and X, B and Y, C and Z. Okay, and here for the secondary winding, and you can see the normal letter A, X and B and Y and C, Z. And of course, you can see how to connect in delta. You know, A star, you know already. That's concept. Okay, and because we take the 3 ends of the winding are connected together, we get here. And of course, if you look at this one, you don't see the neutral point of this winding. It means that for this winding, we don't get the neutral point. And of course, for the primary winding also. And star. Okay, and how to define the number 12 here? If you want to define the number 12 here, you have to define the phase angle between line-to-line electromagnetic force of primary winding and the secondary winding. Okay, I would like to show you later. Okay, I would like to explain, I would like to teach you later for this. Okay, and of course, so keeping in mind this concept, of course, if you come back to, if you move on to this, okay, this case you can see star and star. Okay, sorry, delta or delta. And now you know what the concept of connecting the winding of the transformer in delta or in star already. If you want the winding to connect it in delta, it means that you have to take the beginning of this phase is connected to the end of another phase. For example, here A, Y, and B, and Z here. Okay. So in the same way, we can do for the secondary winding like this. Okay, and delta number 12. Okay, and of course you can see here star and delta or star. But and now you can see here it's very easy already. You can see here star, of course, star, delta, star. But here, so Y is the number, is the dimensional number. Okay, dimensional number here 11. Okay, and here 11. Okay, and I would like to teach you, and also I would like to emphasize that. Okay, the initially when you look at the figure like this, okay, the figure like this here, okay, you can see it's the same the type of writing, and of course the number here is always even number. You can see the same the type of connecting. Okay, star, and of course and this number is always even number. So even number such as number 12, number 10, number 8, number 6, number 4, number 2. Okay, and of course if you move from left hand side to right hand side, you can see here it's the same connection, star, and the number here is always even number, or number 12, or number 10, or number 8, or number 6, or number 4, or number 2. Okay, number 2. Yes, number 2. And here, you can see here. Okay, and of course when we are discussing about this type writing here, you can see this type writing here, you can see, and the star here, and the delta here, star here and delta here, you can see star and delta here, which because the different type of connecting between the primary wording and secondary wording, and the number here you can see as star or delta, and number here is always dimensional number. It's always dimensional. Okay, dimensional here, which is 11 or 9 or 7 or 5 or 1. Okay, or 1. Okay, and of course when you do the middle term or the final term, of course they will ask you. Okay, they will ask you and they will ask you to insert, to put the number like this, and so in the side, if you look at the diagram of the writing, if you look at, of course for the primary writing and the secondary writing are different type of connecting. It means that we have to define, we have to put the number here must be the dimensional. Okay, dimensional, which can be the 11 or the 9 or the 7 or the 5 or 1. Okay, of course if you put the even number here like number 12 or number 8 or number 10, it's wrong right away. It's wrong right away. Okay, and of course here you can see, okay, delta star, you can see because the different type of connecting winding of the transformer, we can see, of course, the number here must be dimensional. Okay, must be dimensional. Of course, you can see, and the idea is that, and now we got already the number of vector group, number 12, number 11 here, and what is the phase angle? What is the phase angle between the line-to-line electromagnetic force of primary winding and secondary winding? It's very easy. So you can see normally, you can see from the number 12 here, it's very easy for us. So you can take the number 12 multiplied by 30 degrees. 30 degrees. So why do we have to multiply by 30 degrees? Of course, I would like to explain to all of you later. Okay, maybe in next slide you can understand very well about that. And of course here, okay, you agree completely with me by multiplying 30 degree, okay, 30 degree with number 12 here. Also we can see, for example, number 12 here is mean that the phase angle between the electromagnetic force of the primary winding and the secondary winding is equal to 360 degree. And of course here you can see, if you take the number 11 multiplied by the 30 degree, we get, okay, we get what? We had 330 degree. Okay, 30 degree. Okay, and keeping in mind this concept, okay, and now I would like to show you the way of defining connected winding group of the transformer. Okay, for beginning, I would like to show you for the single phase transformer. single phase transformer. Okay, single phase transformer will be simply for all of you to understand. Once you understand very well about the single phase transformer for defining connected wiring group, okay, and then we move on three-phase transformer easier. Okay, here have a look at the figure on the left hand side. You can see here for the single phase transformer with the primary wiring, which can be high voltage or the low voltage. Okay, you can see, for example, the primary wiring, okay, draw with the red color, okay, like this, and of course the secondary wiring in the blue color. Okay, here you can see here, if the direction of the wiring like this, you can the direction of the wiring like this, okay, and also the direction of the wire of the secondary wiring like this, okay, due to the current flowing in the primary wiring or the secondary wiring, we get the generated magnetic field in the iron core. Okay, and now, so if we consider the electromagnetic force of the primary wiring as AX, okay, and of course for the for the electromagnetic force of the secondary wiring like AX here. Okay, so and now we draw the vector of AX primary wiring and also AX of secondary wiring. Okay, you can see here AX here, for example, for the beginning AX, yes, for the primary wiring. Okay, and then we fix, okay, we fix AX, okay, we fix AX, and then we can draw the electromagnetic force of the secondary wiring according to the primary wiring. Okay, you can see here, because the AX for electromagnetic force of primary wiring, and of course electromagnetic force of secondary wiring, the direction of this one, how to define. Okay, because you can see the direction of the current flowing in the primary wiring like this, and of course here we can see the same direction, and for that we get the same direction of electromagnetic force of AX here, So if we consider the electromagnetic force of primary wiring like AX as the minute hand of the clock, okay, of the watch, okay, minute hand. You can see the minute hand, yeah, okay, and of course for the second wiring electromagnetic force of this wiring, okay, as a hour hand of the watch, okay, of the watch here, okay, watch here. You can see here is corresponding to the minute hand, and here is corresponding to the hour hand. If you look at here, you can see the watch is showing you the 12 o'clock. Okay, showing you is the 12 o'clock, like this one, 12 o'clock here. Of course, if you look at this watch, you can see for each, and for number 12, you can see we get 12 section, 12 portion for it. So the 12 portion, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 section. For each, you can see the angle for each section here between number 12 and number 1 here, and the angle here is the 30 degree. You get 30 degree, okay? If you take this as a standard, and then you can compute the angle phase between number 12 and number 1, and number 12 and number 2, or even number 1 and number 2, or number 2 and number 3 here. You can see the phase, the angle is the 30 degree. And for that, you can see here, and the watch is showing you the 12 o'clock here, okay, because here we are cursoring for the single phase. So that's why we get the vector group like the I denoted I here, okay, I source I here is 12 o'clock here, okay. It means that the phase angle between the electromagnetic force of primary wiring and the secondary wiring is the 360 degree, because we already take number 12 multiplied by 30 degree. So why do we have to multiply by 30 degree? Because you can see that for each of its phase angle of portion is equal to 30 degrees. So that's why we get Okay, of course. So keeping in mind this one, and now if we change the direction of this, we keep the primary wording as before. Okay, before, or even for the direction of the current. Okay, and now we change. You can see we change the direction of this wording. And how to do? You can see for beginning, if we keep the position of primary wording and also the direction of the current of this wording, we get the direction of electromagnetic force of this wording like this. Okay, and now if we change the direction of this wording, it means that you can see electromagnetic force of this wording is not like this. You can see the direction like this, for example. Okay, let me move on to next slide. You can see if we change direction, you can see like this one. Okay, you can see the change direction like this. And this one, you can see here. As the direction of this one, come back to this. If you look at this one, you can see the watch. Okay, the watch showing you. The watch showing you the watch showing you the 6 o'clock. At 6 o'clock here, it's very easy for you to deduce the first angle between the primary wording and the second wording is the 180 degree. You can, if you take the 6 multiplied by 30 degree, as I said before, and otherwise, if you don't want to take number 6 here, okay, 6 multiplied by 30 degree, okay, it's very, you can do another way, but you can see here. And from this, okay, you can see from this electromagnetic force, okay, you can take, okay, you can use, you can rotate from here to here. You can see 180 degree. It's the same. It's the same, but I think it's a simple way by taking, okay, by taking the number 6 multiplied by, okay, multiply by 30 degree, we get the final result. Okay, we get the first angle between the primary wording and between the electromagnetic force primary wording and the secondary wording. Okay, and of course for the single phase of the transformer is very easy. It's very easy. Okay, and now I would like to show you. Okay, and now I would like to show you the way of determining a three-phase transformer. Three-phase transformer is more complicated. It's more complicated than a single-phase transformer. Okay, like this. I think for this way, okay, I think so. Keeping in mind this diagram, okay, I would like to show you. You can see the beginning. If you look at this one, you can see yes. And for the primary wording, three-phase of primary wording are connected in star. Okay, everyone knows this one. Okay, and of course, how about the secondary wording? If you look at here, yes, of course, three-phase of the secondary wording of this transformer are connected in star also. But what is the difference is that and for this one, when they are connected in star with the neutral point and here. Okay, and of course, it's very easy for you to write star and star here. But number 12, you don't know in advance. You don't know in advance. Okay, our responsibility is that we have to define this number. We have to define this number. How to define? Okay, we have to define this number, but how to define? Okay, I think I would like to come back and now I would like to come back to whiteboard and to show you. I think for that it's better for all of you to understand how to draw the vector group of three-phase transformer. Okay, and now I would like to remind all of you that if you want to define the vector group of the transformer, okay, you have to look for the line-to-line electromagnetic force of primary winding and the secondary winding, and then you compare two vector of this one, and from the vector group, okay, you can find the phase angle between the line-to-line electromagnetic force of primary winding and the secondary winding. Okay, I think let me come back to here. You can see the concept here. In order to determine the connected winding or group or vector group depending on the type of textbook. Okay, textbook. We need to define a single phrase between the line-to-line electromagnetic force of primary winding and the secondary winding of the transformer. Okay, you should remember this concept. Okay, even in the middle exam or the final exam, they will ask you this question to answer, to select the best answer for this question also. Okay, and for that, yes. Here, okay, I think now I stop sharing. Okay, I stop sharing this one. I come back to our whiteboard to guide you how to draw, how to build the vector group of this transformer. Okay, it's very, very important. So even if you look at the textbook or you go to the internet to see some video clip, how about to define the vector group transformer, I think you can also understand. But I think it's the best way for all of you, yeah, to take care of our lecture. Okay, to take care of our lecture. Okay, take care of my teaching also. Yeah. Yes, I come back to our. Sorry. Yes. Principle here. Yes. Yes, come back. Whiteboard. Yeah. It's a little bit late. Okay, now I delete all of this here. Okay, now. So you can see now, for example, I make a copy like this, and then I come back here, I make paste. I don't know how to paste. Maybe no. Okay, here you can see, for example, here we get three-phase transformer. So here I use this one. You can, yes, okay, here. So I think it's not beautiful, but we don't get another way. This one, for example, here, and also we get the transform primary winding of the transformer like this. I'm trying to write more beautiful, but it's unfeasible to do that. You can see, for example, here A. Okay, you know, because I'm and C here. Okay, and of course you can X here. You can see X, Y like this, and that's like it. Of course, here we get A, normal A, B, okay, sorry, B, and C here. Of course, you can see here we get, and sometimes they wrote N or 0 depending on each computer. And of course, here you can see the like this. Okay, for example, if we get the direction of the winding from the beginning to the end, and also it's the same. For example, it's the same. Okay. So for example, you one of the student told me that yesterday. Okay, yesterday you were ejected. Okay, by vaccine. Okay, by vaccine. Okay, and if you feel tired, okay, you can you can turn out. Okay, you can turn out, and then you can keep your health. Okay, here you can see how to define. You can define how to define the vector group of this transformer. Okay, and of course, if you look at this one, it's very easy for you to deduce. And of course, we know the types of wiring like this already. Yes, nice this and So because this is the neutral point, okay, and of course, and the assignment, okay, you can see that the assignment, okay, must define the number here, okay, and in order to define the number here, I would like to show you, okay. The first, you have to build the vector group, the electromagnetic force between primary winding and the secondary winding, okay. You can see, if you look at this one, we had a vector like this, vector group like this, okay. For example here, okay, so why do we get like this? You can see, and here A, for example, and here B, for example here B, and here C, and here A, and here you can see X, E, Y, sorry, Z here, okay. You can see X, Y, Z, X, Y, Z, A, B, C, because you can see the phase angle here, 120 degree, you know already, because you can see for the three-phase transformer, for each phase angle each between the phase A and phase B is the 130 degree here, okay. And of course, and now our assessment must find the light-to-light electromagnetic force of this winding, okay. Sorry, like this one, like this, okay. So we have to define electromagnetic force of primary winding, okay. Light to light, so light to light, you can find A or B or B or C or A or C. So that's the reason why, and here, so I intend that, so I would like to find the light to light electromagnetic force of phase A and phase B, and for that I would like to locate B here, and A here, and C here, okay. And of course, for other students, so with that, if we want to define phase B and phase C, it's okay, no problem, or even for phase B or phase C is no problem, okay. And once you fix the diagram like this, and now we have to draw the light-to-light electromagnetic force of secondary winding according to the primary winding here, okay. You can see, and now you can see, if you see the phase A, okay, and now so phase A and X, you can see the direction of phase A from beginning to the end. Of course, here A and X, okay, sorry, A and X, E, and that here, for example here, okay, and that here. You can see in the same direction of the winding, and of course the vector AX must be the same direction and in parallel with the vector AX here. You can see the AX here, and of course AX here must be the same direction and also in parallel with this one. You can the same direction and also parallel. Let me draw like this. You can see, and here, so normal A and X here, you can see must be the same direction and also in parallel. Sure, okay. And of course, for phase B, you can see phase B is the same also, the same direction, and also it's also parallel. It's also parallel with the BY here, you can see, and here we get the BY here, X, and you can see EY here, B here, and of course you can see the CZ, okay, and CZ must be here. Let me write it, C and Z here, Z, and of course you can see, and here of course that is the A light-to-light voltage, okay, light-to-light electromagnetic force of the secondary winding here, okay. And now let me move on this electromagnetic force here. You can see and move on like this, and here you can see AB here, move on here, okay. And I move on here, so I move on like this, and I move on like this, we get like this, here, A, E, sorry, because I'm using a mouse, so you can see here. And now if you take here, you can see this 360 degree. Okay, 360 degree. So if you look at this one, you can see that what is showing. What time is this? According to you, what time is this? What time is this? You don't know. Yes, all right. It's very exactly 12, and for that we get here number 12 here. Okay, number 12 here, and the phase angle between the light to light electromagnetic force of primary winding and the secondary winding is you can see here at 360 degree, or otherwise you can take number 12 multiplied by the 30 degree, you also get the same result here. Okay, and of course we keep the same like this, and now we keep the same the direction of primary winding here. And now I delete this one. For example, I delete this one here, and now I change the direction of this one from like this. You can see like this. Okay, you can see here number what? You can see. So when we change the direction of the winding here, it means that the direction of light to light electromagnetic force of secondary winding it changed also. It changed, so it means that you can see and electromagnetic light to light electromagnetic force of secondary winding here for beginning before like this. Okay, and now come back like this. Okay, come back like this. Come back like this. It means that come back like this. So do you think what time is it? What time is it?
It's like 6.
Exactly. Okay, exactly right answer. Okay, and number 6. It means that the phase angle between the electromagnetic force a primary winding and the secondary winding is 180 degree. Okay, and for that here, so we get here number 6 here. Number 6 here. Okay. Of course, and now I change anything here. Okay, we get number 6 or number 4 or number 2, which can be not number 5 or number 11 or number 9. Why that? Because it's the same connection. You can see the same connection, star and star, and of course the number here must be even number without being dimensional number. Okay, I think this one you understand. I think this one you understand what I'm saying. And for that, for next, for next maybe next week. Next week I would like to show you. I would like to show you the way of defining when the transformer getting the different type of connecting. Okay, and now it's high time for us to stop talking our lecture here. Okay, have a nice lunch. Okay, have a nice lunch. See you next week.
See you,
Okay,
teacher.
goodbye.
Okay, goodbye. See you next week.
Goodbye, teacher.
Okay.
Goodbye, teacher.
Goodbye, all of you. Okay.